Dimensionality reduction. The complexity of any classifier or regressor depends on the number of inputs. This determines both the time and the space complexity and the necessary number of training examples to train such a classifier or regressor. In this chapter, we discuss feature selection methods that choose a subset of important features, pruning the rest, and the feature extraction methods that form fewer new features from the original inputs. Introduction. In an application, whether it is a classification or regression, observation data that we believe contain information are taken as inputs and fed to the system for decision making. Ideally, we should not need feature selection or extraction as a separate process. The classifier or regressor should be able to use whichever features are necessary, discarding the irrelevant. However, there are several reasons why we are interested in reducing dimensionality as a separated preprocessing steps. In most learning algorithms, the complexity depends on the number of input dimensions d as well as on the size of the data sample and for reduced memory and computation. We are interested in reducing the dimensionality of the problem. Decreasing d also decreases the complexity of the inference algorithm during testing. When an input is decided to be unnecessary, we save the cost of extracting it. Simpler models are more robust on small datasets. Simpler models have less variances, that is, they vary less depending on the particulars of a sample, including noise, outliers, and so forth. When data can be explained with fewer features, we get a better idea about the process that analyzes the data, and this allows knowledge extraction. When data can be represented in a few dimensions without a loss of information, it can be plotted and analyzed visually for structure and outliers. There are two main methods for reducing dimensionality: feature selection and feature extraction. In feature selection, we are interested in finding k of the d dimensions that give us the most information, and we discuss the other d minus k dimensions. We're going to discuss subset selection as a feature selection method. In feature extraction, we're interested in finding a new set of k dimensions that are combinations of the original d dimensions. These methods may be supervised or unsupervised depending on whether or not they use the output information. The best known and the most widely used feature extraction methods are principal component analysis (PCA) and linear discriminant analysis (LDA), which are both linear projection methods, unsupervised and supervised respectively. PCA bears much similarity to two other unsupervised linear projection methods, which we also discuss, namely factor analysis (FA) and multidimensional scaling (MDS). As examples of nonlinear dimensionality reduction, we're going to see isometric feature mapping, ISOMAP, and local linear embedding (LLE).